So this is the 5th edition of WITS at Intuit, and this is the first time that we had a call for papers. And we are extremely happy that we had north of 40 papers that we received. And we also had a committee which followed a very detailed selection process. And this was chaired by Siddharth Kumar, who is our principal engineer, principal data scientist at Intuit. And we will also be having a panel judging the presentations today for the Best Paper Award. So over to Siddharth for the rest of the segment.
Hi all, it's a pleasure to be here to introduce the speakers for the afternoon session. So we're going to have some 4 talks which are highly illuminating, and it's going to be in line with the rest of the talks that were there in the morning, which were also great. Uh, so first we're going to have Chaitanya Lingaraj, and just going to give you a brief introduction about Chaitanya. Uh, Chaitanya received her MTech degree in Power Electronics from BMS College of Engineering and pursuing her PhD in National Institute of Technology. She is working as an assistant professor in the Department of Electrical and Electronics. And she has an interest in several topics on machine learning. So this includes things which are like multi-level converters, energy storage, robotics and automation, electric vehicles. She has co-authored 8 IEEE conference papers and 7 journal papers in the aforementioned areas. And she also is serving as the vice chair of the IEEE Power Electronics Society in Bangalore and is an active member of the IEEE Industrial Electronics Society. So please welcome Chaitanya. So I'm going to be just giving you a brief intro of the talk itself. And this talk addresses challenges posed by limited data availability in time series forecasting, particularly in domains like battery technology, which is the focus of her work. And synthetic data generation is crucial to supplement training sets when it's actually in sparsity. She will discuss the importance of synthetic data and improving the model performance. The second part of her talk will focus on EMA regularization, a technique that is used to dynamically adjust boundaries during training to enhance model stability and improve forecasting accuracy. Thank you so much for being with us, and please proceed.
Thank you for the kind introduction. Hello, everybody. So post-lunch, I hope you all don't go sleep. From the introduction, you all must have got to know I'm purely from an electrical engineering background. So what am I doing here in a data science conference? So we are trying to find and explore ways how we can solve energy domain problems using data-driven solutions. So today I'll be presenting our work, that is tackling data challenges in energy domain and how synthetic data could be an answer for this. So this work has been carried out by one of my students, Niharika Joshi, and Janamejaya Chennegowda, who's with Rome Semiconductors, and I am Chaitanya Lingaraj from BMS College of Engineering. So this is going to be the outline of my presentation. I'll brief the background of electric vehicles and batteries, and also give a detail as to what is the key problem and what could be the solution that is required. I'll also discuss about the data details, that is the battery data details, and also explain the method in significant detail that we have used for two types of models, and also discuss some of the results of two models. And I'll be concluding giving the insights and results that we have obtained from our work. So let me first introduce you all to the lithium-ion batteries. So we all know that there's a large drive to electrify the transportation sector. So there is an indine need to electrify all modes of transportation now. Now, why is that need? Because there is a large curve or rising levels of pollution we are trying to address. Okay, so the solution for this, what we have found, is electric vehicles. So these electric vehicles have a major part of having battery management system. Basically, the battery is the heart of your electric vehicle. So these batteries, we just found that lithium-ion batteries are the best choice for electric vehicles. The reason being, these lithium-ion batteries have very high energy density, and also they have a very long lifespan. And if you are owning an electric vehicle, so it is always necessary that you estimate the range. Basically, if I have charged my vehicle, I want to know for how many kilometers I can travel with one charge. Okay, so that is one major important thing. That's a concern we all keep thinking of. It's basically a range anxiety most of the electric vehicles have. Okay, so how to deal with it? Okay, so to deal with it, we have to do some estimations. So estimations basically would require parameters such as voltage, current, the temperature at which your battery is working, and also something called as the state of health or state of charge. Okay, so voltage, current, temperature, I think most of you all understand vaguely what that is. So let me explain about the state of health and state of charge. So what is the state of health? So it is how long your battery can be used. Maybe for 8 years, maybe for 5 years to full effect, how long your battery can be used. That is state of health. The next important component is the state of charge. Okay, so to understand state of charge, we can just have an analogy with our usual cell phones that we use. So we would have seen some of the times that if your cell phone battery may be indicating a battery capacity of say 5%, and you get to see that suddenly your phone may shut down. Okay, and some other cases wherein you get to see 1% of battery, but still your phone may run to next 5 to 7 minutes. Okay, so this is all related to state of charge. That means whatever is indicated, the estimation is not proper. It had to serve for some more long duration with 5% charge, or what you were expecting in 1% charge, maybe the next 2 minutes, but that is not happening. Okay, so this is the major problem. We have to estimate the state of charge. So maintaining adequate state of health and state of charge in batteries is a very critical parameter. So how can this estimation be done? There is no direct measurement of state of charge. They always depend upon the voltage, current, and other parameters. And there are indirect methods. So long we have been using indirect methods such as physical modeling or measurement equipment techniques and things. But now we are interested in data science. How can data science come into picture and help us know the state of charge of a battery? So the problem that we are facing is there is a lack of battery data. Now, why is that there is a lack of battery data? Because this battery required a measurement equipment which is very expensive. And the battery manufacturers generally don't release the battery data because of the confidentiality concerns and things. Okay, so they don't release the data. Now, how can we know that data-driven techniques can be a solution for such a problem. So we are in need of generating the data. And one more thing is that if we think, let me buy a battery and let me do some cycling on it, that means charging and discharging, and try to take out all the important points of voltage and current at specific time. But I may not get the decent amount or good quality data very immediately. So this may take some 8 to 12 months basically. So that's a long period. So I'll have to wait for 12 months to get the battery data and then try to use my algorithms on it. So the basic problem, the key problem we are facing to use any data-driven technique is the lack or scarce of the battery data. So what is the solution we are planning or we have found to is that we can use synthetic data. And also while using the synthetic data and applying some regularization techniques to this, we can also have a high quality synthetic data. So how does our data basically look? So these are the voltage, current, temperature, and the state of charge parameters. So if you can see, the voltage is somewhere varying from 2.2 to 4 volts, and the current range is hovering somewhere close to 0 and 10. Minus is basically this data is taken for a discharge cycle. Okay, so negative doesn't mean it's a negative current. It just means that we are considering the data in the discharge cycle. So for one complete discharge cycle, what we are getting to see is that there is a slow rise in the temperature, but the estimated SOC is being decreasing. So we are trying to work on the SOC estimation. How can we work? Based on all the taking consideration into all the parameters such as voltage, current, and temperature. So say suppose I have charged my vehicle, I started traveling, and the charge contained within the cell is going on decreasing. So what should I do now? I have to find a relationship to estimate this SOC with respect to the available range. So that is what we are trying to do. So this, whatever data I was talking about, is essentially a time series data. So here, for an example, here the time series data, what we have considered, let's say we're using an encoder-decoder architecture approach. So the encoder input, considering 96 point, and the decoder input is going to have half of the encoder input, that is 48 points, and the next for 24 points will be padded zeros. Okay, so this is what we are interested in. This is going to be our estimated data. So coming on to the encoder and decoder architecture. So here we can see that this encoder architecture is having the multi-head PropSpace self-attention mechanism, and the concatenated feature of this map will be given as, will be fed as the input to the decoder, to one of its head. And the inputs of the decoder, what we see here is XD, which takes into account of the encoder input as well as the padded zeros. So finally, what we require is the output, which is just about the decoder block. That is the what you see in the yellow marked things are the predicted data what we want to do. Now, how can we see this data or the encoder decoder mechanism with respect to our voltages? Okay, so we have just taken an example of voltage here for this paper, wherein we see that we've got 6 cycles of voltage, and where we have considered 4 cycles to be the encoder input, and then the decoder input is being considered, that is a part of the encoder input, but we are actually interested in the timestamp of 300 to 500 seconds, which is actually the prediction sequence. Okay. So in order to do that, we are using different approaches to generate synthetic data. But after generating synthetic data, we wanted to see if we can get a high quality synthetic data. For that, regularization comes into picture. So there are a lot of deep learning and attention-driven algorithms which are there, which have shown remarkable success in the time series forecasting. But due to the dynamics of the time series data, the deep networks are still suffering with the unstable training as well as the overfitting issue. Basically, I have tried to train my model for one set of battery data. I take another set of battery data, it should work well according to me, but it is not doing so. Basically, it is not generalizing well. That is the problem. So we try to use some regularization technique. So to check the model works fine for any unseen data as well. So in order to do this, we need to address the overfitting issue in time series forecasting. So there must be an effective regularization method that will dynamically provide the error bounds of training loss in the time series forecasting, and this method consistently should improve upon the existing state of art time series forecasting method as well. So basically, in the whole training phase, we've got two networks. One is the source network, G theta, and the target network, G tau, both with having the same architecture but different weights, that is theta and tau. So the target network tries to update its weight based on the EMA technique, that is exponential moving average technique, with respect to the weights of the source network, whereas the source network tries to update its weights based on the gradient descent update, and the wave empirical risk formula for that is being indicated below. So this is about the regularization part. So basically, we have done two things here. First, we try to generate the synthetic data because there is lack of data, and we try to also add in some regularization technique so that we get a better quality data. So this error bounds, which should be dynamically adjusted according to our regularization technique. So we have used the EMA technique here. So the target network G tau, as I already mentioned, is updated with the exponentially moving average and of the source network with a decay rate of alpha being equal to 0.99. Now, what is the battery that we have worked on to estimate this? So we have considered a pouch cell battery, and this is the capacity of the battery. The capacity is 3360 milliampere hour, and the chemistry is lithium cobalt oxide. The nominal voltage being 3.82 volts and the maximum voltage being 4.4 volts. We've got the data set. This is what is available, open source. We've used the data sets. There are many data sets related to this pouch cell. We have used one of that to do our estimation and regularization. This can also be tried on different data sets that are available. So how are we evaluating? Again, it's the error matrix evaluation what we are doing. That is the mean squared error, MSE, mean absolute error. The formulas are given with the equations 1 and 2, where yi is the ground truth value and yi cap is the predicted value. So some of the results when we are just trying to make a comparison based on the error matrix. So what you see in the blue line is basically just the models that we have used, the transformer, basic transformer model and transformer with the regularization technique. Where if we see and compare with the MSc results, we find a fairly good results with the transformer plus EMA technique. But MAE results show that the errors are very much low when compared to that of the plain transformer technique. So we tried incorporating the similar kind of approach also for the autoformers, and we again get to see this is of MSc values, the comparison. The dashed line is basically giving the autoformer plus EMA graph, and for the MAE it is again the dashed line, which is showing that there is considerable amount of a decrease in the error values. So this is the results for the pouch cell. We are also trying to work on different battery data, but the problem here is there is no battery data available for us to implement the algorithms. So the main reason, one of the other reasons why I'm here is I would also want to know from the data scientists. You all are all in the data field as to is there any other way or any technique that you have come, you have got to know using which we can again try to do some things related to battery, because EV is a very trending field now, because we are all trying to electrify most of the vehicles. So concluding, I would say the access to battery data is challenging due to the time, cost, and all other issues that I just mentioned. And we have tried to present a technique to produce synthetic battery data over the long sequence with minimal errors. And the regularization method is very beneficial for long sequence synthetic data generation. We also have released this code so that it's open, so that some of you all can try to do some research on this as well and come up with the new approaches as well. So that is it from my side.
Thank you so much for it. It was an excellent talk. Now I'd like to field questions from the audience. So, did anybody have a question there?
And okay, and I will also want, yes.
Hey, thanks for the talk. So I wanted to understand a little bit more on the regularization part. How did you go about doing that? And
Okay.
so you also generated some synthetic data with the available data set, right?
Yes, yes.
So was it for one battery, multiple batteries, and uh, how much was the actual data and what was the synthetic
Yeah,
data?
actually, suppose basically if you're talking, if we have 100 data points, we can estimate to another 20 data points in future. That is the basic ratio we are able to do it with the battery data set. So the drive cycle, what we had seen only 4,000 data points. That's a limited set if we are considering. For 4,000 plus 1,000 is what we are able to generate using the synthetic data. Now we again try to loop this and try to go on adding the data. That is what we are planning to do henceforth. So we have just tried this for the pouch cell batteries, the battery parameters that I had just indicated. Yes, forecasting.
Okay,
Yeah.
Hi, nice presentation, firstly. My question is about the synthetic data generation that you've done. How did you go about generating the synthetic data? Was it coming from the literature, or were you doing some behavioral modeling, hybrid modeling for the battery?
We've tried basically from the literature, because this was initially a student project of mine. So they started with the literature survey and tried doing what is in the literature. Now they're working with the behavioral models and things, but we've still not got good enough results to move out with that, but they are trying some other model on that as well.
Thank you.
Yeah, hi. Nice presentation, first of all.
Thank you.
So I actually, let me introduce, I'm directly working in battery data. I'm working in Green NBFC,
Yes.
who loans electric vehicles. So we are taking the IoT data through API streaming, and we try to predict the user behavior and the health of the particular vehicle. So on your presentation, I just wanted to understand. So user behavior, in the sense, it depends on the usage, how the user is behaving, and based on that, the state of charge and state of health will also
change,
vary. So does that apply? So, and I'm also not talking about the time series algorithm. I'm more like talking about classification algorithm. And it also depends on which user is a bad user and which user is a good user. So will that be applicable if that data generation and regularization?
Yeah, that can be taken as one of the parameter, but right now we have just focused on the basic parameter, voltage, current, and SOC. There's no user behavior considered yet. Okay, that feedback can be taken into our algorithm. Based on the cases, we can improve the algorithm and try to get the result. I think that can be done, provided this algorithm is only for the time series.
Only for time series.
Time series, whatever
Yeah.
we have discussed here. But I think there is also a paper which we have referred to, which is employing the classification part, what you have told. That is there in the literature. So they're working on it.
Yeah.
But I don't see the user behavior taken into account yet.
Okay. So my point is like even now we are also facing the data issues, the scarcity issue, but I don't think the synthesizing the data and the regularization will be the optimum solution in
No,
our
it
case.
is one of the solutions, sure,
Okay.
but it
But
we
not
are
in context of the user behavior and the defaulting.
yeah, but I think we can still try to consider it in future.
Okay.
And see what will happen. If we don't give a step first, trying to synthesize and regularize, we will still be at the very first point where we don't know what to do without data. We are
Right.
just trying to get the data first and then try to work on the algorithms and thing, and also add the feedback of user. I think it can be done, but it will take a lot of time.
Yeah. Thank you.
Hi, this is Bhavna. I work for HP Print Business, right? So I don't know if this is a question or a information that I want to share. We worked on a similar problem statement where we are trying to analyze what is the average useful life of a printer, right? Which is very same as how long will a product survive or when will a product die, or basically you have to define the problem statement, right?
Yes.
So we did analyze too much. We did check on a lot of data that report back to us from our printers. But then we realized machine learning is not the answer. Classification algorithms are not the answer. It's about the foundation, and I think it is statistical techniques that you have to dig deeper into. So we finally found out that it's a survival analysis problem where you have to plot the data and understand if it follows the exponential curve or a Weibull curve. Basically, it's a survival analysis, right? So our problem statement initially was to understand we will have to predict for every printer when will this printer die, so that we target customers right at the time so that they don't leave our brand, right? So
Yes.
yeah, I mean, this is a business. But then we had to change our problem statement because we cannot go at a serial number level. It's impossible, privacy concern and stuff like that, right? So then it comes down to analyzing it at an aggregated level. So the problem statement changes to uh, at the end of n years, how many devices will survive or how many will be dead by then, right? And that is where the distribution and stuff comes into picture. And we realize first we thought it's exponential curve, it's declining exponentially, and then it followed a Weibull curve or something. And then we have a AUL that exists and we are using it.
So where's
So
the, is it, got it.
yeah, so that's just the information that I wanted to share.
Thank you
And
for
it's
sharing
it's
that.
not easy.
Yes, it's not easy.
There is a lot of error, but it's very informative for the business for sure.
Yes, yes. Thank you for that information. I'm actually looking for a solution here. Basically, while I'm trying to present, I was thinking like, okay, there'll be a lot of people here working in the data domain. So if anybody will have some idea, maybe later at least you can connect to me. I will drop my email ID too. Yes.
Sometimes, right, synthetic data, right, may not be applicable for the particular business. See, we are not allowed to do any kind of a synthetic data. If that is the case, right, even if it is, for example, there is a product launch, okay, new product launch, and we don't have a similar data points with other product, right, what we will do it, we take it at the regression point of it. So include other attributes and take it as a regression equation. That's a one way that you can predict it instead of a time series forecasting. And time series forecasting, you really need to have a continuous data. Or if you are going with a time series forecasting with a lesser data set, add more multivariates. That will be like a more useful way of doing it, because we largely work in the time series forecasting.
Thank you so much.
Thank you so much, guys. And thank you so much, Chaitanya. So one last question and then we'll move on.
Yes.
But it's been an excellent discussion so far. Please.
Sorry for throwing such a tantrum, but I was just going to ask you, you motivated the problem saying that, modeling based approaches to synthesize the data have some shortcomings. And when you're doing a data driven approach to synthesize battery data, trying to overcome those shortcomings. Can you just
Not
me-
exactly
exactly.
overcoming the shortcomings. We are trying to, because now data science is coming to boom. The measurement equipments are very expensive, and we don't have enough data from the manufacturers. We are trying to link the electric domain field with the data science. While we are trying to do that, how can we get data is what we are trying to address, not trying to address the shortcomings of the other methods, basically.
Got it. So
But
your
in
other methods are
industry-
inapplicable because you don't have data. Is that the right way to think about it?
You get the data, it takes a lot of time in the industry. But since we are trying to work with algorithms, we want an immediate data that can be available for the algorithms.
I see. So your modeling approaches are not able to generate data.
They're able to generate data, but we want more data for better results. Because with we all know that with limited set of data, the accuracy is well and good. But when you go for a long horizon and long set of data, then the accuracy may also get hit. So we want to test our models again on those lines. That is the reason.
Got it. And your mean, so your MAPE measures, all of them are on actual data, or what is your difference? How are
That
you
was on
measuring
the
MAE?
actual data is what we had considered for the pouch cells.
Thank you.
Thank you.
Thanks so much, Shona. So excellent talk again, and thank you for the discussion as well to the audience. I think that was a very productive discussion.
Thank
so
you for the
much.
opportunity. Thank you.
Thanks. Allow me to introduce the next speaker. This is Harini Anand from PS University, a CSE undergrad and a Google Kaglex mentee interested in computational cognition, and a developer intern at Niramai Health Analytics.